In this highlight video, we're going to talk about some really cool concepts, and that has to do with chirality and stereogenic centers. After watching this video, you should be able to classify molecules as either chiral or achiral, and we're going to learn how to identify what are called stereogenic centers. Objects are chiral if they're different from their mirror images. An important example has to do with our hands. So if we take our left hand and we reflect it into a mirror, what we see in the mirror is essentially an image of our right hand. And if we try to superimpose our left hand and our right hand, we will find out that we cannot superimpose both of our hands. We know that already. And because of that, our hands are chiral objects, because chiral objects are any objects that are different, non-superimposable than their mirror image. Conversely, achiral objects are any objects that are superimposable with their mirror image. For example, we could take this bottle and we reflect this bottle into the mirror, and what we get is essentially the same bottle. If we superimpose them, they superimpose perfectly, and so the initial bottle was achiral. We can think of other examples of achiral objects as well. So what could we think about objects that are different from their mirror image? Well, if our hands are chiral, then certainly our feet are chiral. Right? We have a right and a left foot. And in fact, anything that we put our right or our left hand into are chiral as well. Things like gloves, maybe a baseball glove or a baseball mitt. Shoes. What else could be chiral? Well, a good example are scissors, right? You can have right or left-handed scissors. Golf clubs. They could be right or left-handed. So any of these objects are chiral because they would be different from their mirror image. So what are some other things that would be achiral objects? Well, we could have something like just a ball or a sphere would be achiral. Right? A water glass. We reflect that into a mirror. The glass would be the same as its mirror image. Most chairs might be achiral. Something like a brick, right? A fork or a spoon. We don't usually have right or left-handed forks or spoons. And so all of these objects would be the same as their mirror image, and so they are achiral. Molecules can be chiral or achiral as well. And so we can analyze them in the same way as we analyze the objects on the last slide. So what we want to do is compare each of these molecules to its mirror image. So let's imagine putting a mirror right here, and we'll draw the mirror image structure. Okay, so here we would have a carbon. We'd have this H that's shining or pointing towards the mirror would be pointing toward the mirror over here. We have an H that's pointing away from the mirror. We have this methyl group that's pointing towards us. So it's going to be pointing towards us in the mirror image as well. Right? And the chlorine is pointing back. Right, so now the question is whether these are the same or different. What do you think? Well, remember, it doesn't matter whether the wedged bond is to the left or the right of the dashed bond. The wedge is just pointing forward and the dash bond is pointing back. So in fact, if we took the structure on the right and we slid it over on top of the structure on the left, they would perfectly superimpose. Okay, so these two structures are the same, and so this molecule is achiral. All right, what about the next one? Let's draw this here. There's our mirror. Let's draw our mirror image. Now the OH, the alcohol, is pointing toward the mirror, so it would be pointing back towards the mirror in the mirror image. The H would be pointing away. One methyl group is pointing out of the plane towards us, so it would still be pointing out of the plane. And we have another methyl group pointing back from the plane. Now what about these two? Same or different? Well, can we just slide one over onto the other one? No, we can't do that because the OH in the left structure is on the right, the OH in the right structure is on the left. So we can't just slide it over. Can we do anything else? Well, in fact, if we make an axis right here, if we rotate this molecule around that axis, I'm going to redraw it over here, by 180 degrees, that's going to rotate the OH to the right, the H to the left. We still have one methyl group coming forward, one methyl group going back. And so now these two structures are the same. All right, we can just slide the one on the right over onto the one on the left. So these are the same. So what, is this molecule chiral or achiral? This one is also achiral. So what does it take to make a chiral molecule? Let's try this one more time on the one at the bottom. So here's our mirror image. Just like before, we have our OH pointing back toward the mirror, H pointing away. We have, I'm going to draw the ethyl group over this way with a wedge, just because it's easier. Remember, it doesn't matter whether it goes angles to the right or left. And here's our CH3. What about those two? Are those the same or are they different? Well, the OH is just like above, right? The OH is pointing to one side, it's pointing to the other side of the other one. Let's try the same thing that we did in the last one. Make an axis here. We rotate around this by 180 degrees. And we now have our OH on this side. When we do this, though, the ethyl group, which is on the front, when we rotate it by 180 degrees, it's going to rotate onto the back. I sometimes think about it as not only rotating, but just flipping it onto the other side. So like this was like a pancake or something, and I put my spatula underneath it, and I just flip it over, right? So whatever's on the top flips to the bottom, whatever's on the bottom flips to the top. So the ethyl was on top, and so now it's on the bottom. The methyl was on the bottom, so now it's on the top. So now let's compare these two, this and this. Are those the same or are they different? Well, the H and the OH, they match. What about the methyl and the ethyl? No, those are backwards. So these two are still different. All right, so that means that this molecule, is chiral. All right, because it's different from its mirror image. So in fact, we have two different structures now, and these two molecules are stereoisomers of one another. Right? They have the same molecular formula, but they're different. That makes them isomers. They're different just in their three-dimensional orientations. That makes them stereoisomers. And because they're mirror images, that makes them a very special type of stereoisomer, and we refer to these as enantiomers. So why is it that only the bottom of these three molecules on the left side is chiral? Right? What's different about this structure right here? Okay, well, the difference is that this is the only case where this carbon right here has 4 different groups attached. Okay, and that makes it a special type of carbon. Carbons, or really any tetrahedral atom, are called stereogenic centers when they're bonded to 4 different groups. It's not just 4 different atoms, it's 4 different groups. A molecule that has a single stereogenic center, these are sometimes called chiral centers as well. If it has one stereogenic center, it will be chiral every time. If a molecule has more than one stereogenic center, it may be chiral, or it may not be. We'll see what controls that in an upcoming video. So let's look at these 4 molecules across the bottom and again decide whether they're chiral or whether they're achiral. Let's look for stereogenic centers. So let's look at the structure on the left. Okay, here's a carbon here. Does it have 4 different groups? All right, it has an H attached to it. It has an OH attached to it. It has a methyl group, and it has an ethyl group, so we would say it has 4 different groups. That makes this carbon a stereogenic center. And that makes this molecule chiral. Okay? What about the next one? Does that have a stereogenic center? Well, sometimes what it's good to do, what can help, is to make sure, if we think there's a stereogenic center, make sure to draw in any missing atoms. Right? So let's draw in the hydrogen right here that's not shown in the initial structure. So this carbon has an H, it has an ethyl, and what else? It has 2 methyl groups. So those are both the same, right? So there is no stereogenic center in this molecule. This is achiral. Okay? Be sure not to be fooled. Just because there's a bond that has a wedge or a dashed line, that doesn't automatically mean that there's a stereogenic center. Let's look at the next one. All right, again, let's draw in the missing hydrogen. Here's a missing hydrogen going back. Does that carbon have 4 different groups? Well, no, because we have 2 ethyl groups. These are both the same. All right, so again, this is achiral. All right, what about the last one? Okay, here's our missing H. This one has a methyl, it has an H, it has an ethyl, and what's this group here? It has a propyl. So this has 4 different groups. This molecule has a stereogenic center, so this molecule is chiral. Let's do just a couple more examples. Chiral or achiral? What about the one in the upper left? All right, let's draw in any missing atoms. that might be important. Here's an H. Is that chiral or achiral? Well, it has an OH, it has an H, and then as we look at this ring, if we go this direction or if we go this direction around the ring, both of those sides are the same. All right? So this is achiral because it doesn't have a stereogenic center. Now, another thing that we can see on this, another way to think about this, is because that OH here and this H here, really the OH is directly in front of the H. We skew them just to the side to cheat a little bit so we can see them both. So in fact, this molecule has what we call a plane of symmetry that goes right down the middle of the molecule. Okay, and when a molecule has a plane of symmetry, it will be achiral. Right, so now let's look at the next one in the upper right. Okay, let's draw in the missing H. All right, does this have 4 different groups? Well, it has the OH, it has the H, it has an alkene, a double bond, and it has just an alkyl side. So it has a CH2 over there, it has a CH on this side. This has 4 different groups. This one is chiral. So by adding this double bond here, where we didn't have it in the last example, that broke the symmetry. There's no longer a plane of symmetry, so this molecule is chiral. All right, what about the lower left? Let's draw in the missing hydrogens. I like to do that every time just to make sure I don't get mixed up. So there's 2. Does this molecule have stereogenic centers? Yes, there's one here and there's one here. So it has stereogenic centers. Does that mean it's chiral? Not automatically. So what else do we look for? The other thing we're going to look for is a plane of symmetry. Does this molecule have a plane of symmetry? Yes, it has a plane of symmetry that goes right down the middle of the molecule like this. Because we see exactly the same thing on each side of this plane. The OHs, so this OH, if that was a mirror, if it reflected into the mirror, it would see this OH over here. So because this has a plane of symmetry, this molecule is achiral, even though it has stereogenic centers. This is a very special circumstance. Okay, so a molecule that has more than one stereogenic center but is achiral is called meso. Okay, so meso like miso soup. All right, so we can have molecules with more than one stereogenic center that are still achiral. What about the last one on the right? Okay, just like the one before, here let's draw in our missing atoms. Here's this H comes forward this time. Are there stereogenic centers? Yes, there's one here, one here. Is there a plane of symmetry? No, not this time, because this OH is pointing up and the other one is pointing back. So if we made a plane down the middle, they wouldn't be reflecting each other. So this molecule is chiral. In this video, we've learned a couple of important points. One is that molecules are chiral if they are different from their mirror image. And the second thing is that stereogenic centers, which are formed by having 4 different groups around a tetrahedral atom, they make a molecule chiral if there's one of them, but if there's more than one, we have to watch out for symmetry and the possibility of having a meso compound.